green.
Oh, really? Even from that direction?
No, it doesn't, because the lens.
Yeah.
Then he tried the other lens, and the other lens spills over quite a bit. Couldn't use that either.
Move the projector forward.
We should have, yeah.
I'm trying to think of what slide that.
We have another group that's
Small printing on this.
It's a box on the left side.
on security.
They have a curve?
So I claim I have.
No.
Wasn't there more for steel?
No, that comes nice. That slide is nice with amorphous steel. It's got two pictures, I think, next to each other.
And the last group to classify it.
I said there was one reason. I was going to say we got one group to make sure that you louse it up so that you know what you're doing, right?
About halfway through the talk.
On the not contingency, not if you're all that out, that there's no one. Do you want to go through with it?
Well, you know, I, as a matter of fact, we do want to record it. So I would say we do it for the camera. That's up to you, I guess. Speaking of Bill Dagberry, I don't know if you would have to eat their breakfast. They have to come upstairs.
These people are casual about the time.
Well, it doesn't. Oh, yeah,
8:50 is off.
Yeah.
More Ruben's time, so we've got one audience.
Chinese. Those are nice with the colors.
That came out good.
Yeah, they really
we kind of threw those in the last moment. We needed something to sort of show that stuff's really good.
Of course, you haven't got it exactly the same format. I think you're past that already. Yeah, you're past it. That's more interesting. I don't remember now. But don't worry about it. The people here will be able to read it fine. These people right here. It's just that I was standing by the projector and I got trifocals still, so it doesn't help.
There's plenty of light.
I say, yeah, it's uneven at this point. But doesn't matter.
Let there be light.
Was.
As a part of our Centennial program, we've tried to bring to you accomplishments and items of interest in those areas of electrical and electronics engineering that we feel affect the public broadly. Yesterday we have covered areas such as electronics and defense, electronics and health, and the pervasion of computers and the forward thrusts in supercomputing. Today we want to cover two other areas that we think are extremely widespread in our society today and that I'm sure you're aware of. First is electrical power. We want to cover areas of where that's going and what effect the issues are having on you. The second area we'll cover later is telecommunications. But for our first session, we will have three speakers who will be moderated by Lionel Barthold. Lionel Barthold is the president of Power Technology, a company in upstate New York. And he has also been the president of the Power Engineering Society of the Institute. Lionel?
Thank you very much. Dick Gowan, in his opening remarks for this comment, went back to review the history of IEEE, this being our centennial, and his early slides illustrated that the beginnings of the Institute tied themselves to telegraphy and to electric power. So it's obvious that this 1984 year represents the 100th anniversary of the power industry also. So it's a mature industry, contrasting to some of the technology that was discussed yesterday, but it's still an industry that is seeing a lot of change technologically, and we have a panel today that's very well positioned to address those changes. I think before starting on that, it's important to think a little bit about the context of application of this technology, because the power industry in the last decade has really changed very dramatically. Load growth, which was traditionally very steady and very strong, dropped to zero and is now at a very low rate. Generating capacity is in surplus. Cogeneration is in some cases turning customers into suppliers, really, in part. The nuclear industry is stalemated. Acid rain has come to the top of the industry's agenda. And the whole industry who has developed a strategy that's based on conservation of oil, that industry now finds itself with in the midst of an oil surplus. I think that the mood in the utility industry, however, is at this point very positive. It's very open, it's very constructive, and very receptive to new technological changes. And those changes you'll hear about from this panel. I think we're fortunate in having a panel that consists of a variety of backgrounds, an electric utility, a major architect engineering company, and a major manufacturer. We're going to break the subject matter down into three parts. The first will deal with the power generation, the second with high voltage distribution, or high voltage transmission, and the third with the distribution of power and the customer interface. You have in the kits, I think, some details on the background of the speaker, so I'm going to make my introductions very brief. The program will begin with remarks by Arthur Lotz. Mr. Lotz has a variety of backgrounds in the Ebasco Engineering Services Company. He is currently Group Vice President for Engineering, and I will at this point introduce Mr. Lotz. Art?
Good morning. I couldn't help but think when Lionel mentioned the 100 years of the IEEE to reflect upon the fact that when I was a bright, starry-eyed young engineer coming out of college, I was hired by a man at Ebasco Services who had been the mechanical engineer who worked on Thomas Edison's Pearl Street Station. So that between that gentleman, his career, and my career, we have covered the whole history of the electric utility industry in the United States. In the past 10 years, we've seen a tremendous awareness of our nation's dependence upon energy resources to meet the demands of our industries and our way of life. No one could have predicted the impact which the actions of OPEC countries' oil pricing policies would have upon American business and individuals. The reaction to these policies and the simultaneous worldwide recession has had a dramatic impact upon the ability to forecast either total energy or electrical energy requirements. And as Lionel pointed out, for almost 2 decades, net electrical energy production grew at an annual rate of 8%. Reserve margins to cover the potential loss of electric generating capacity at time of peak load demand often was as large as 40%. Now, however, all of that has changed. The growth rate for the latter half of the 80s and later is being forecasted to be about 3%, and reserve margins are rapidly being depleted at levels less than 25%. This lower rate of growth has caused over 130,000 megawatts of scheduled new generating capacity to be canceled, which would have been placed in operation in the period in the mid-80s through the mid-90s. What will happen if the forecasts are low? It is estimated that 0.5% change in the growth rate will require an additional 64,000 megawatts, or the equivalent of 128 500 megawatt power plants, to be built by the mid-1990s. Taking an average time span of 10 years from initial license application to commercial operation, it appears that we could be at the brink of an energy crisis. In 1983, electrical energy consumption grew 3.6%, and peak load demand grew 8%, based upon information released by the Office of Technology Assessment in their report, Nuclear Power in an Age of Uncertainty. I think that change in the load growth rate is very significant, and as you see already, our forecasts are sort of out of line, but then again, that may be the norm for swings of that nature. The options that are open to resolve this dilemma have been greatly reduced. Design and construction of gas and oil-fired plants, which formerly took about 4 years, is no longer an option due to the restriction placed upon the firing of gas and industrial boilers by the Power Plant and Industrial Fuel Use Act, and the 5-fold increase in the price of oil. Nuclear power plants, which in the late 60s and the early 70s could be designed and constructed in 6 years, and at the cost not significantly greater than a coal-fired plant, no longer a viable option in the current public and regulatory environment. Bob Shearer, the head of the U.S. Committee of Energy Awareness, has stated, "No utility executive in the country would consider ordering a nuclear power plant today unless he wanted to be committed." Hydroelectric power plants may be considered a viable option, except that the environmental impact of such developments are considered by some organizations to be unacceptable, and thus any major undertakings are subject to prolonged licensing hearings. Lastly, we turn to the coal-fired plant option, which could be problematic depending upon the regulatory positions which may evolve from the acid rain issue. In addition, a significant increase in coal-fired plants in a relatively short period of time could have some restrictions relative to either the ability of the railroads to transport the coal due to the condition of rail facilities, or that ability to develop new coal mines under current environmental permitting requirements. What then are our options, and what are the technologies which can be applied? What do we know, and how can that help address this potential dilemma? Researchers continue to work in the fields of solar energy, wind power, fuel cells, and so forth. However, the developments to date, although significant in a relative sense, are not far enough along to place these energy conversion systems into economic commercial facilities, which could make a contribution to the electric power generation requirements of this country in this century. We must therefore look to technologies which may be applied in a more conventional manner. We see the power plant built in the late 50s and the 60s as a potential source of reliable generation. It has been estimated that if we could defer retirement of these units by just 5 years, over 18,000 megawatts of additional capacity will be available in the 1990s than had been forecasted. In conjunction with this program, a unit performance improvement program to regain lost capacity due to degradation may also be instituted. These programs may require significant analysis of the condition of the equipment and systems to determine their physical condition. When those units were installed, we did not have some of the instrumentation which is available to us today, nor did we have the diagnostic capabilities, nor the mathematical simulation techniques that modern computer technology provides us today. These latter techniques may also be applied to later vintage plants, wherein it is entirely possible that opportunities may be found to increase the rated capacity of a plant beyond its original design. Another option that is available to extending the useful life of some plants is the firing of coal water or coal oil mixtures in boilers which have originally been designed for either future conversion to coal from initial gas or oil firing only. The technology is known that would permit this option to be developed, but it is economically dependent upon the regulatory position of having to retrofit an air quality control system on existing boilers which did not previously have this requirement. It is estimated that approximately 20,000 megawatts of generating capacity are candidates for this application, which could enhance the probability of not retiring oil-fired units and increase their electric generating hours. The firing of coal mixture opens the option of coal pipelines as a means of transportation. The general degradation of our nation's railroads has been a major concern as to their ability to transport coal without a major upgrading of some of the lines, which might be either too costly or too time-consuming. Economic studies indicate that pipelining of coal might be the most attractive energy transport system as compared to either railroad or transmission lines. Although coal pipeline ventures have not been successful in obtaining the right of eminent domain, such as been granted oil and gas pipeline companies, the technology is available for utilization. If this obstacle can be overcome, and surely it must, if transportation of fuel becomes a blocking issue, then this might be a significant contribution to power generation shortfall. We have discussed here several options relative to existing plants. Now let's look at new facilities. The trend in general appears towards consideration of smaller plants so as to achieve a better fit to the rate of load growth and potentially reduce the overall design and construction period. In this area of activity, it is a natural corollary to then think in terms of gas turbines, combined cycle, and cogeneration facilities. It is estimated that approximately 15,000 megawatts of power production facilities of this type will be installed over the next 10 years. Relatively few gas turbine and combined cycle, that is a combination of gas and steam turbines, have been installed in the United States, but they do represent proven technology. Cogeneration is a challenge to the engineer, since development of cycles which produce the quantity and quality of steam required by the industrial owner and the electric power required by the owner and the utility is significantly different from the basic central power station known to most engineers in the electric utility field. This is the realm of the industrial engineer and the manufacture of smaller boilers, turbines, and auxiliary equipment. This smaller size facility is brought about in part as a result of the Public Utility Regulatory Policy Act of 1978, which stipulates that the facility cannot be more than 80 megawatt in size. This would result in considerable redirection of concentration on equipment development as this activity increases, particularly since it's been forecasted that in the neighborhood of about 150 to 200 plants may be built in the next 10 years. Since time may be a factor, as the electric load growth scenario unfolds, it seems appropriate to touch upon the subject of computer-aided design, or CAD. The utilization of computers in the engineering and construction of power plants is in its infancy, but is emerging quite rapidly. The objective of this approach is to develop a system which will result in efficient retrieval and reformatting of data from a common data bank. Through the storage of applicable codes, standards, design guides, and criteria in the computer, production of plant drawings can be implemented with the application of appropriate programs. From these data, which are generated from the drawing production, key documents such as material and equipment lists can be produced. Quantities for cost estimating can be developed. Drawings can be readily revised, with data resulting from one drawing revision being automatically noted on all other affected drawings, and so forth. This programmatic research will increase the probability that information will be accurately communicated from one activity to another, thereby reducing significantly the time now spent in manual deriving and transforming data, as well as the manual checking effort required. As design information becomes available, it is conceivable that it will be transmitted electronically between engineer and client, engineer and construction site, engineer and equipment vendor. Storage and retrieval of design documents and data will be significantly improved both during the design process and subsequently as part of the plant records for operation and maintenance. The absolute value of this type of a program is unknown at this time, but is sure to have a positive impact both in time and cost. In summary, it may be concluded that technology has been developed and is emerging, which should be able to address the electric generation requirements for the balance of the century, if the deviation is not too far from the forecast. We will have the opportunity to apply this technology if the public and regulatory environment is conducive to its implementation.
Thank you, Art. Thank you very much. We have time for some questions, so I'll ask if there are any from the floor. I'd like to take the chairman's prerogative and ask one myself. Art, I'd like to ask you where you think the U.S. nuclear industry is going from here. We've seen such a lot of confusion and discouragement in that field. Where do you think it's going?
I believe that if you look at the numbers that people keep presenting to the public, the electric utility companies are being somewhat crucified, you might say, through excessive costs and excessive overruns in schedule. This is not a subject which basically is their fault. What we have lacked is the setting of standards and criteria which would enable the plant to be designed to specific standards which would be then acceptable by the NRC and not being constantly ratcheted as we develop the nuclear power plant itself. We have taken an industry which was very much in its infancy, and we have caused that to be developed as we're actually putting it into commercial operation. I believe that we have come a long ways in knowing what should be in a power plant, and therefore, if that's the case, then let us spend the time in the development of the standards and criteria. And in that way, then we all will know what we're designing and building to, and in that time frame, then we would be able to establish a program which would permit design and construction of power plants in a much shorter time frame than what we are seeing at the present time. And I do believe on that basis that if there is this positive approach to things, then the nuclear option will return to us in the electric utility industry.
Okay, thank you. Any other question,
How
Alice?
long would that take, and what would the roadblocks be in order to have standardized plants that have a change in the regulatory process?
I did not say standardized plants, because there are many options within the plant itself. There's the boiling water reactor and the pressurized water reactor, and between pressurized water reactors you have different types of plants again. What I did say was establishment of standards and criteria, and therefore we would not have the tremendous backfitting and retrofitting that we keep on seeing in the current day power plants. I believe that if we set forth a period of time, approximately 5 years, we could do exactly what I was referring to, and in that way then sometime in the turn of the next decade, we should be in a position to bring that industry back up on its feet again. I only say that because I have the personal experience of having been responsible for the design and construction of nuclear power plants in Japan. And in the time frame that I lived and worked there, I found that the Japanese did set these standards, and we did design the facilities to those standards, and as a result, the world's records as far as the time frame required to design and build a nuclear power plant are held by companies who worked on those Japanese projects. And they were approximately 1/2 the time frame that it takes to build a power plant here in the United States.
It's very interesting. Any other questions for Mr. Lotz? Let's move on to transmission technology then. And we're fortunate to have Dr. Fred Ellert from General Electric to discuss that with us. Fred has a broad background in GE product developments, including the direction of development of a high voltage DC thyristor valve, which has been the cornerstone of HVDC technology that he'll include in his remarks. Dr. Ellert is currently General Manager of the Electric Utility Systems Engineering Department of General Electric. Fred?
Thanks, Lionel. Could you please turn the slide projector on? It's all set. The electric power transmission system in the United States has been a key factor in the achievement of high reliability and low cost of electric power. In order to understand the potential future role for transmission, it's perhaps worthwhile first to take a very brief look at the past. As you are all undoubtedly well aware, the principal function of the transmission system has been to transfer electric energy from generating plants at various locations to the load centers. The use of large generating units or plants in conjunction with the transmission network permits not only economic dispatch of power within regions during normal conditions, but also the transfer of power between regions during emergencies. Thus, transmission connections of adequate capacity between separate power systems makes possible the integrated operation of these systems with resulting performance and economic advantages. And the principal economic advantage to date has been a reduction in the reserve generating capacity required on the system. The ability to use the lowest cost fuel, whether it's coal, nuclear, or hydro, has also become increasingly important in recent years. Prior to 1973, the key driver for transmission additions was generation additions, which were tied to load growth. Between 1920 and 1945, the peak load growth averaged 6.3% in the United States. From 1945 to 1973, it accelerated to about 8% per year, and from 1973 on, it's averaged only 2.9%. You're all aware of that. As the load grew, the power transmitted over the new transmission lines added also grew. Both economic and performance considerations required that higher transmission voltages be utilized to transfer these larger blocks of power, as indicated on this slide. As you might expect, at the present time, there are more circuit miles of lower voltage transmission lines, but the circuit miles of higher voltage lines have increased rapidly from the mid-1960s to the mid-70s. As indicated, AC transmission lines rated 765 kV have been in operation since the late 1960s. Fewer new lines operating at 765 kV have been constructed since 1975 than was earlier expected due to the reduced load growth. After World War II, interest also developed in the transmission of power by means of direct current. DC transmission offers economic and performance benefits when transmitting power over long distances overhead, under bodies of water with cables, or between AC systems that are not synchronized. The use of high voltage DC transmission grew particularly rapidly worldwide after the early 1970s, when reliable high voltage solid state converters first became available. By 1995, about 50 gigawatts is expected to be in commercial operation worldwide. Let me now talk about the recent technical advances and what they will mean to the utility industry and the public. Recognizing the importance of the transmission system in the overall electric power network, a great deal of research and development on both transmission lines and transmission equipment has been underway for many years. The Electric Power Research Institute alone has sponsored over 200 projects in the transmission area. Recent transmission line research at the High Voltage Transmission Research Facility in Lenox, which was formerly called Project UHV, has focused on line design for AC voltages in the range of 1,000 to 1,500 kV. Important factors investigated included environmental effects, losses, and insulation requirements. The potential trade-offs between performance and cost also were of primary concern. In order to gain actual operating experience, the Bonneville Power Administration constructed an 1,100 kV prototype AC line, shown here on the left, and operated this line for several years to gain some knowledge, first-hand knowledge. As a result of extensive research in both the United States and abroad, the basic design parameters for 1,100 kV lines are well established. Such lines can economically transfer in the order of 5,000 megawatts on one circuit. Research has also been conducted at the High Voltage Transmission Research Facility on high voltage DC lines. This is a photograph of their test facility. In addition to conventional line parameters normally considered, the effects of ions were also investigated, and voltages between 600 and 1,200 kV were studied. As a consequence of this research in the United States, as well as that in the Soviet Union, the basic design parameters for DC lines up to plus and minus 800 kV are well established. Such a line would typically carry in the vicinity of 3,000 to 6,000 megawatts on one line. Because of environmental and regulatory delays, electric utilities are now seeking practical alternatives to constructing new ultra-high voltage lines. There's a desire to make more effective use of existing transmission lines and existing rights of way. The power transfer capability of lines which are not already operating at their thermal limits can be increased by the addition of series or shunt capacitors or the use of phase-shifting transformers. Rights of way can be made to carry more power by raising the voltage on existing lower voltage lines, converting AC lines to DC, or compacting the lines. Research is presently underway on hybrid lines where AC and DC lines are on the same tower or the same right of way. The line on the right in this slide can carry 50% more power than the one on the left. On the other hand, line compaction would permit more circuits in a given space. High phase order is one form of compaction which has been investigated and offers considerable promise. This is a photograph of an experimental 138 kV six-phase line which has been built and used to verify the predictions of its electrical characteristics. Overseas, a 400 kV six-phase line is being looked on as a potential alternative to a more conventional 800 kV line. A considerable amount of research and development work has also been underway on high voltage transmission equipment. Basic concepts, design concepts, have been developed for 1,100 kV AC equipment. An area of particular interest has been high voltage DC transmission. This slide shows the 250 kV solid state converters of the Square Butte project in the United States. Since that project was commissioned in 1978, a great deal of additional work has been done. Thyristor converters rated 500 kV and 2,000 amperes have been developed for commercial application in the United States using both air and liquid cooling. A 600 kV project is underway in Brazil, and the Soviet Union has been developing a 700 plus minus 750 kV project for their country. Direct light firing of thyristors has been demonstrated to be practical, and the development of much higher voltage cells, up to 5 kV in one cell and 100 millimeters in diameter, has resulted in lower losses, which of course is very important. Greater control flexibility has been achieved through the use of microprocessors and sophisticated new control functions for multi-terminal operation, for real and reactive power control and for damping of system oscillations have been developed. Converter transformer losses have been reduced, and zinc oxide arresters make possible much better protection of equipment against overvoltages. As a consequence, HVDC systems are more cost-effective than ever before and provide greatly improved performance. HVDC should play an increasingly important role in power transmission in the future. At the present time, in North America alone, almost 8,000 megawatts of HVDC transmission is in service, and another 5,000 megawatts is currently in the design or construction phase. These installations are indicated by the pink lines on this map. A very economical way to increase the power transfer capability of an AC line is to install capacitors in series with the line so as to reduce its electrical impedance. Using zinc oxide discs with high energy handling capability, the reliable protection of series capacitors against overvoltage is achieved by connecting a series parallel array of such discs directly across the capacitors. This slide shows a prototype of such equipment installed on the Bonneville Power Administration system. Several installations of such protective equipment are now underway in the United States, and others are planned. Another means of increasing the power transfer capability of existing transmission lines is the addition of shunt capacitors in the form of conventional switch capacitor banks or the newer so-called static VAR controls. Static VAR controls, which essentially consist of controllable inductors and capacitors, were initially applied to control voltage flicker produced by electric arc furnaces, and more recently static VAR controls have been applied to control rapid voltage fluctuations on power transmission systems and to improve the stability of large power networks. Static VAR controls consist of thyristor switches, sometimes in conjunction with mechanical switches, to control the amount of inductance or capacitance connected to the transmission line for purposes of high-speed voltage regulation and increased power transfer. Recently, research work has also been underway on the application of zinc oxide devices on transmission towers to reduce their vulnerability of the transmission lines to flashovers caused by lightning. This is particularly important in areas where the earth resistivity is high, such as on rocky ridges. Special strutted arresters shown here, they're the horizontal units between the conductors in a tower, are now installed on a 138 kV transmission line of the American Electric Power System to verify the reliability of such devices. This will enhance the overall reliability of electric power systems by making them less vulnerable to interruption during the lightning season. Let me wrap up by saying a few words about the outlook for transmission. In order to better appreciate the role of transmission in future power systems, one has to understand the present and future electric utility business environment. One of the key factors is load growth. And as you've already heard, recent forecasts suggest that the average annual load growth from 1982 to 1992 may be in the vicinity of 3% per year, while the growth rate from 1992 to the year 2000 may be only 2% per year. This would indicate significantly less in the way of transmission additions. However, another important factor in the utility environment is the pressure to reduce electricity costs. The electric utilities very successfully reduced electricity costs for decades prior to the oil embargo and remain dedicated to keeping electric energy costs as low as possible. One method of accomplishing this is to utilize lower cost fuels for power generation. At the present time in the United States, the average costs of oil and gas are significantly higher than the average cost of coal in terms of dollars per million BTU. This suggests that electricity costs could be reduced significantly by displacing oil and gas-fired generation by generation using lower-cost fuels, also, of course, hydro and, in some cases, nuclear. Electric energy could be transferred very economically from those areas where surplus, low-cost generation exists to other parts of the country where expensive oil and gas are being burned. At the present time, more than 100 gigawatts of electric power is being generated using oil and gas with an average annual capacity factor of about 45%. The fuel cost alone for this generation is $20 billion per year. These generating plants are located principally along the coast in New England, the Mid-Atlantic states, Florida, Louisiana, Texas, Oklahoma, and California, as indicated by those circles on the map. On the other hand, surplus coal-fired generation, and I want to underline surplus, exists principally in the east central part of the United States. Some surplus hydro and nuclear power also exist. Unfortunately, existing transmission lines are not capable of transferring any significant amount of additional energy between these regions. More energy could also be imported from Canada if the peak transfer capability to the United States was increased to about 35 gigawatts from the presently planned value of 14 gigawatts. And this is indicated by the small arrows on the map at the interface between the United States and Canada. Most of that capability is in the eastern part of the United States because Hydro-Quebec has a lot of hydropower. A preliminary study indicates that about 45 gigawatts of the oil and gas-fired generation in the U.S. could be displaced by power from distant power plants using lower-cost fuels. The annual saving in the United States would exceed $4 billion and would pay back the cost of the additional transmission required in less than 2 years. The additional lines that would be needed are shown on this map in yellow, and they're principally from the east central part of the United States branching to the east coast and down into Texas and Florida, some also on the west coast. Due to the long distances involved, more than half of this transmission could be in the form of HVDC transmission. The ultimate beneficiary of such a transmission expansion program would be the ratepayer due to the reduction in electricity cost. From the utility's viewpoint, such an investment must be measured on the basis of the expected return. Unfortunately, these opportunities probably will last less than the normal 30-year write-off assumed for other utility investments. In fact, some utilities that have excess coal-fired generation are only willing to make 5-year contracts. Therefore, in order to justify such an investment, a new financial arrangement is needed whereby the utilities can recover their investment in a few years out of the anticipated savings. The utilities and the public utility commissions must work together to develop such arrangements. Once this has happened, the utility industry can move forward to expand the transmission system for the economic benefit of all the users. It's very clear that the utility business environment has changed considerably since the mid-1970s. The growth in load is much less rapid, the financial health of many electric utilities has suffered, and the environmental concerns are greater. However, there are still opportunities for reducing the cost of electricity by taking advantage of fuel price differentials. But to achieve these reductions, additional transmission is needed. Due to the significant investment in research and development on transmission lines and equipment in recent years, the technology exists to meet this demand. Only the economic incentives need to be made available. Thank you.
Thank you very much, Fred. That $4 billion saving is a very attractive target. Are there any questions, Alice?
Taking the lead in trying to accomplish the goal that you're talking about. What are they doing?
A number of utilities have already started down this road. For example, New England Power has a project underway that at the moment will be importing about 700 megawatts from Hydro-Quebec, and that project will be expanded to approximately 2,000 megawatts. They are buying hydropower from Canada at 80% of the cost of their own oil-fired plants. And I believe there is an arrangement in Massachusetts whereby if a utility takes actions to save costs, they can keep 2/3 of the saving, whereas the ratepayer gets 1/3, I believe, until the plant or the installation is paid off. There's also a project underway on the west coast of the United States whereby the Bonneville Power Administration, in conjunction with the California utilities, is hoping to bring more power down, hydropower down into California to displace oil and gas. The existing Pacific DC intertie which is operating at about 2,000 megawatts now, will be expanded to over 3,000 megawatts by pushing the line up to its thermal limit. And there are other projects I could mention. There's quite a few. It's on an ad hoc basis. The most significant problem is, well, there are two. One is that if the utilities were to put this investment in the rate base, they pay it off over 30 to 40 years. And some of these opportunities probably will only last 8 years. The second is that if they need to build a new line, if it takes 5, 6, 7 years to get approval for a new right-of-way, the opportunity will have evaporated. So there has to be an understanding on the part of the public and the public utility commissions that there has to be a better way to handle these kind of opportunities to reduce the electricity costs.
Any other questions? Fred, you mentioned the very considerable amount of work that's been done in developing ultra-high voltage, 1100 kV to 1500 kV range. Do you see any application of that technology in the United States in the next 10 years or so?
I don't believe so unless the load growth picks up significantly above the levels that people are presently predicting.
Okay. Let's move on to distribution then, and the interface with customers for electricity. One of the leading technologies in that field is load management, and one of the leading companies in that subset of distribution technology has been the Pacific Gas and Electric Company. Ron Thompson, who will address this subject, has had a variety of assignments in engineering departments at PG&E and is currently in the rate department as director of load management, and he will address this subject for us. Ron?
Thank you, Lionel. Excuse me. Thank you, Lionel. Good morning. As Lionel said, one of the most exciting areas that is currently facing electric utilities is in the distribution area, primarily because of some of the recent changes brought on since 1973 in trying to develop more efficient systems and working with our customers to provide various types of options that they can reduce their electric bills. Although this is a Centennial conference, we have to realize that a lot of the developments have taken place in the last 10 years. So many of the remarks that I'll make today are directed towards developments that have taken place during this last 10-year period. During this last 10-year period, there has been a shortage of capital, and some of the options that both Art and Fred have been talking about on the generation or the transmission side of it are vying for the same dollars that could be used in the areas of what we're calling load management or distribution type changes to improve the efficiency. And because the utilities have been short on capital, and also because of the relatively short lead times with respect to changes in the distribution system compared to generation and transmission, a lot of the activities have been taking place in this area. Can we have the slide projector on, please? Very good. Thank you. I think, first of all, if we look at the characteristics of the electric utilities in 1972, I'm going to compare those to what we're seeing right now. In 72, we had a continuing expansion of our generation facilities. The fuel costs were relatively insignificant. We were talking about $2 for a barrel of oil compared to $40 today. It was a decreasing cost business in that the marginal costs were less than our average cost, so it made economic sense to continue the expansion of our generation facilities. In addition, as both Fred and Art mentioned this morning, there was a continued growth in consumption. We were up and around 7% a year in both peak and energy, and now we're down in the 2% area. That's contrasted what we're seeing today. We have a limited growth in new construction. At the same time, there's a continued growth in demand. Now that obviously is a catch-22 because you can't continue to have your growth in demand increase at the same time there's no increase in construction. Therefore, one of the obvious solutions is we have to make better utilization of our existing facilities. I'm not sure if you can see that slide from back there. I apologize. From here anyway, it's fairly light. Can you see that slide okay from the audience? Okay. The emphasis on electrical distribution has been on improving the efficiency. We used to look at a kilowatt of loss on the electrical system as being costing about $70, and currently it's up to around $2,000. So in a decade, it's increased considerably. So therefore, you can see the importance of improving the efficiency on our system. Now, there are many components to the electrical distribution system, and I can't go over all of them. What we thought we'd do is just take a very common element on the electrical distribution system, the distribution transformer. There's about 20 million of these on pole tops or in underground vaults throughout the U.S. We thought we'd go through a couple of the recent advances here to give you an indication of what's being done. First of all, as far as purchasing of this equipment, most utilities have developed fairly elaborate economic models, which they're being used in evaluating various designs on transformers, the various designs of the transformers, economic considerations, and therefore the purchase decision may not be on the lowest cost now, but on the one that over the life will produce the lowest cost for the utility when losses are considered. Another major advancement has been the development of a new type of metal that's being used in the core of transformers. Right now it's in the experimental stages, but it really shows a lot of promise, and this is the amorphous steel. Basically, the steel is cooled, when it's in the molten state, it's cooled very quickly, and therefore the transformation characteristics are much better than the standard types of steel that are currently being used. As you can see, the top curve, where the M4 silicon steel is a typical type of steel used in the cores of transformers as opposed to the amorphous metal. It's about an 80% improvement in the transformation. Now, you may say, well, what does that have to do with the overall efficiency? Well, if you consider that if we can make a 1 to 2% improvement in the overall efficiency, thereby reducing the loss, if you're looking at a total fuel bill of something like $40 billion for the U.S., a 2% increase would be about $800 million per year. So there's some significant improvements and reductions that we can achieve just by improving the efficiency on, say, our distribution transformers. Some other areas, we've really taken advantage of the space age technologies that have come out. Fiber optics are becoming commonplace now. Microprocessors are being used in distribution control of our operations. And we're using these to improve the efficiency, but also to reduce the manpower, so the total cost to the consumer are going down. This slide is a SCADA system, which is a supervisory control, alarm, and data acquisition, which is basically bringing data back in, telemeter data back in, so that we can operate with this, either remote control from a substation or from a demand control center. Now, most utilities do have these SCADA systems in place now. The smaller utilities are using them for remote types of control. The larger ones, like my own company, PG&E, we use it for our demand control, where we telemeter in information and use it for economic dispatch of our power plants. But we're really using these real-time systems for control and improving the efficiency. Now, so far we've been talking about efficiency on distribution system, but the real breakthrough, and this has occurred in the last 10 years, has been we've been moved beyond the customer meter. No longer are we just satisfied with supplying the customer to his meter, but we're concerned on how that energy is being used beyond the customer's meter. We're looking at the residential applications. This is an example of some of the major end uses on the residential side, being it cooking or air conditioning, dishwashing, or water heating. The commercial industrial side, primarily lighting process systems and space conditioning. And on the agricultural side, from agricultural pumping. Now, many utilities, you've heard from all the speakers today, are concerned with the rising growth and limited capacity. And so one way to do that is to provide the customer with rate incentives such that they are willing to shift their usage patterns to a period which is more economic for the utility. And this is intended to exemplify our customers working together with the utility to move that energy off of the peak period and hopefully back into the off-peak period or eliminate that energy altogether. Also, besides helping the utilities from an efficiency standpoint, this sort of an operation is advantageous to our customers because, as we all know, our utility bills have been rising. Customers are beginning to look at alternative ways to reduce that bill, and one way is for them to, I guess bluntly said, taking a different type of electrical service, a lesser quality electrical service in exchange for a reduced rate. The answer to what we're calling this is load management. This is a term that's being coined. There probably could be a better term than load management, but it is one that is intended to represent our customers changing their usage pattern in a way that improves the efficiency of our electrical system. In a recent EPRI survey, in 1977, there were 37 utilities involved in the load management programs, and in 1981 that moved up to 170, and I'd venture to say almost every utility now is involved in some type of load management program. As far as the role of load management, has several benefits. First of all, it improves the system reliability by giving us larger reserve margins. It provides the customers with service options, as we mentioned. It gives them an alternative. Most programs that you see throughout the U.S. are voluntary in nature, so the customer can make the decision. If he's willing to pay a higher bill, that higher quality of service, he can have it. If he wants to reduce his bill, that's also an option. It also contributes to the diversification of our resource mix. I think Art talked about smaller generating plants. And this goes hand in hand. You know, we can, depending upon the magnitude of these load management programs, we can intensify them to match our load growth. It also complements our energy conservation efforts, and we won't even go into the conservation programs to date. As you're probably aware, I think every utility has a whole menu of conservation programs that are also changing the customer usage patterns. But it does complement the conservation programs because we're looking at reducing energy during this peak period of the day as opposed to during all hours of the day, which a conservation program is directed towards. It acts as a short-term contingency resource that's available if we are short on capacity. This is a resource that we can utilize, and there's varying degrees of how we make use of that resource. And lastly, it promotes the efficient resource allocation through a price signal. Customer is given a price signal that at certain times of the day it's costing utility more, and therefore he should try to minimize his use. And we'll go into a little more of that in a little bit. The load management programs, or rate or service options we're calling them, are really broken down into three categories. Time of use rates, where, if you might remember from the previous load curve, the demand for electricity is not uniform throughout the day. It does have its peaks and valleys. I think if you just think about your own living patterns, nighttime you have a minimum use, you get up during the day, it's a hot day, you turn your air conditioner off, you turn it on. I'm too much into load management. You turn your air conditioner on and then you curtail it in the evening, and so we say that we see the same sort of cyclical pattern on our as a total demand for the electrical system. So what we're doing is giving the customer the price signal that during the peak periods of the day it's costing the utility more, and therefore he should curtail his use. During the off-peak periods it's a lesser price, and he's free to use energy at that reduced cost. Interruptible curtailable programs are involved with either automatic interruption or notifying the customer that we are in a period of time in which we need his assistance, and therefore he will curtail or interrupt a certain portion of his load. Direct control programs are involved with actually shutting off or cycling of equipment such as air conditioners or water heaters. Now these programs from the time of use are really directed at all of the sectors. There's time of use programs in the residential, agricultural, and the commercial industrial sectors. This is an example of a Sangamo time of use meter that's one of the major meters that are currently used on residential time of use. The standard kilowatt hour meter that you see in your home costs the utility between $25 and $30. These are costing about $200. Therefore, there has to be some benefits in putting one of these in. On my own